So I'm Kevin, and today I'll present our work from ICCV 2019 CapsuleVOS, Semi-Supervised Video Object Segmentation using capsule routing. So this is a brief overview of what I'm presenting. So I'm going to start off with a brief introduction to capsule networks and compare them to conventional CNNs, convolutional neural networks. Then I'll present on the extension to videos, and then talk about the problem of video object segmentation, and then our CapsuleVOS network. So the introduction to capsule networks. So the motivation behind capsule networks is that CNNs don't explicitly model entities. All right, so what capsule networks do is they add extra structure to CNNs to model these entities. They do this by grouping the CNN activations together as a group of neurons, and these model different objects. Okay, and then thank you. Then routing by agreement is used for these different capsules, these different groups of neurons, to model part-to-whole relationships. So I'll briefly go over what routing by agreement is. So capsules take inspiration from inverse graphics. So let's take regular computer graphics for example. So in regular computer graphics, what we have is a set of instantiation parameters. So for example, we have two objects, right? A rectangle with this position and this angle, and a triangle with that position and that angle. And then it calls a rendering function to render those into an image. Computer vision is ideally the opposite, would be inverse graphics, right? We have an image, and we call some sort of inverse rendering function to get our parameters back, right? So an ideal system, we would be able to take that image and then get back, okay, we have a rectangle at this position and this angle, and we have a triangle here with this angle, right? An ideal system would be able to do that. So what capsules try to do is model these different objects and their instantiation parameters using groups of neurons. So the really foundational works for capsules recently have been two works by Jeffrey Hinton's lab. So dynamic routing between capsules, which is NeurIPS 2017. So basically in this paper, it's a relatively small network, but each capsule is a vector of different neurons, and the length of the vector represents the existence probability of that object which it models, and then the values in the vector represent these different instantiation parameters. And so these networks pass from one layer, these capsules pass information from one layer to another using dynamic routing, which finds the similarities between capsule votes. So this is just a dot product between different capsule votes. If the dot product is similar, that means, or the dot product is high, that means these capsule votes are similar. So that means that the parent object exists. If the dot product is very low, then they're dissimilar, so the capsules don't exist. So I'll go into a brief example for EM routing. So the second paper is matrix capsules with EM routing, which was in ICLR 2018. So this is somewhat different. The idea is still the same. We still have these groups of neurons, and we still have these activations, right? But this time they separate the activation from the instantiation parameter. So each capsule is composed of two things: a 2D matrix, so like a 4x4 matrix with 16 different parameters, which models the different parameters of the object, and then separate activation neuron. So what this activation neuron tells us is between 0 and 1, and it tells us whether or not that object is present in the image at that location.
Can you minimize the recordings?
Oh. I want to do that. Okay, there. So the 2D matrix contains the instantiation parameters, and the activation is the presence probability. And the main difference is the type of routing used. Whereas previously we had a simple dot product, which measured the similarity between votes. This is more complex EM routing algorithm, which is basically just EM clustering. I don't know if you went over that, but it's basically just a clustering algorithm which tries to cluster the different votes into different capsules. So what is capsule routing? So in the EM routing EM routing paper, they have this nice, I took this, it's high dimensional coincidence filtering. So basically what it says is, suppose we have 2 layers of capsules, right? So like in CNNs we have multiple layers. Suppose we have 2 layers. So one is the primary layer, which has some simple parts. You could think of these as, for example, parts of a face. So you have eyes, a nose, and a mouth, right? Let's suppose we have capsules for each one of those, right? And we want to learn the properties of the face. What you can do is you get each one of these capsules to vote or predict what the properties of the face should be, right? Suppose the eyes, the nose, and the mouth are all slanted in one direction. They would all vote for, the face to be slanted in that direction. If they all agree in their votes, right? If the properties of the face are all the same in accordance with all the part capsules, that means that the face probably exists in the image. But if suppose we have some sort of, Picasso painting where the eyes are separated and then, very strange painting, then the votes won't agree. So the face, there would be no agreement in that, right? So here's a simple example. All right, so suppose we have 2 layers, right? And the higher layer, capsule layer has 3 capsule types, right? Capsule A, B, and C, right? Each of the lower level capsules, in this case we have 10 lower level capsules, will cast a vote for each one, right? So this is 2-dimensional, but in practice it'd be like a 16-dimensional vector or matrix. So each one of these is a different vote from a different lower level capsule, and then we have 10 votes for each capsule, right? Higher level capsules, right? For the EM routing, what we'll do is we try to cluster these votes, right? So in the first iteration, this is iterative, we would try to group, find the mean of the votes and some variance, right? And we see, okay, C has a very tight cluster. So B has, not as tight, and then A is seemingly random. So as the iterations of the algorithm, we get further into the iterations, these clusters become tighter and tighter, and then we end up with this, right? And what this routing by agreement will tell us is, for example, A, there was no agreement between these lower level capsules, so the object that A models doesn't exist in that image, right? Because if there was no agreement, then probably these parts don't belong to this object A. B, there was somewhat more agreement, right? It's a tighter cluster, but not that tight, so B might exist, or it has a higher probability of existing than A. And then C, it seems that all of them agreed, so capsule C would have a very high activation, and it probably exists in the image. Yeah.
Would you actually want the capsules to overlap?
Oh yeah, ideally they would all be the same, they would all agree on the same point, but that tends not to happen in practice. But yeah, ideally it would be a single point, all the capsules agree exactly, this is that object exactly, as is. So yeah, so this is like the basics of, EM routing. If you want to get into more in depth on capsules, then I suggest reading those 2 papers that I showed earlier. They really give the intuition behind these capsules and how they work somewhat better. So now I'll talk about extending capsules to videos. So this was our NeurIPS work in 2018. So at that time, in 2018, capsule networks just started coming out. Capsule network papers just started coming out, and they achieved very good results on very small images, right? So MNIST images, which are 28 by 28, then small NORB, which I believe is also 28 by 28. But they were not successfully applied to like higher dimensional data, either images or videos. And even currently, there's not many works that do on larger images, and I think there's very few works that do it on videos. And the reason for this is capsules are computationally costly. That routing algorithm, as you saw, was iterative. So if you have many capsules, then you have to cluster many different capsules, and each iteration will cost more and more memory. So that's computationally costly, which makes deeper networks not be, you can't really fit deeper networks into memory. When we extended capsule networks to video, we did several, we could call them tricks, but which I won't go into details, but basically we want capsule networks for video because on these smaller data sets we're showing, okay, they're able to learn very good representations. So if we learn these representations in videos, that would benefit us, in video understanding. So, that's our work that we extended to videos. The summary of that work is basically we extend capsule networks before they were just 2D, right? And we just extended to 3D. So you could think of it analogously to 2D convolutions. We expanded it to 3D convolutions, but instead of convolutions, we have routing. And so we present like an end-to-end method for video action detection and segmentation, and achieves very good state-of-the-art results on UCF1 and JHNDB, which are popular action detection data sets. I'm not going to go into like the specifics of this paper because I want to focus on the ICCV paper. So that's a brief, introduction to capsule networks and video capsule networks. And now I'll talk about the problem which our paper is dealing with, which is semi-supervised video object segmentation. So semi-supervised video object segmentation is you're given the first frame segmentation of a video and the first frame segmentation. So what you're given is these two things. First, the segmentation of an object in the first frame and the entire video. And the goal of this problem is to segment that object throughout the video. So given this, we want to propagate that segmentation throughout the entire video, right? Even if the camera moves or if the object moves, we want that mask to be tightly, we want to segment that object over the entire video. We're supposed to be. So it's called semi-supervised video object segmentation, but it's important to note all the training data is annotated. So it's a fully supervised method. It's only called semi-supervised because we're given the first frame at test time. So I don't really like the name semi-supervised video object segmentation, but that's what they call it because we have that first frame.
Can you repeat that? Why was it called semi-supervised?
It's called semi-supervised because we're given at test time the first frame, that first frame segmentation. So at test time we're given this and the video, right? So they call it semi-supervised because we're given this first frame. The unsupervised video object segmentation, we would just be given the video and we have to segment the salient objects, basically.
Okay.
Yeah.
Was there any higher level abstraction of annotation given in the test? Like let's say video level you give the annotation like the deer was present in the video.
Yeah.
Was there any let's say weak level was used?
No, we're given this segmentation. I'm not sure I follow the question though. Yes.
Let's say for the test time, is it so the same object should be present in the test video?
Oh yeah. So you're given the first frame of the segmented for the test video, and you're given the video itself, right? You just want to propagate that frame. Yeah. Okay. So it's not a simple problem. There's multiple different, difficulties. So we have, small objects, fast motions, both camera motion and the object motion. There could be multiple objects of interest in a single video. I'll show you some examples later. There could be similar objects to the object of interest. So if you saw the last video, there were multiple deer. So a network might simply just segment all the deer, or the segmentation for that single deer might move over to other deer because they look very similar. There's changes in illumination, object deformations. So when objects move, right, they deform over time, and then some unseen objects. So at training time, we have some set of let's say 80 objects in 3,000 videos, let's say. But at test time, when we're giving new videos, these objects might never have been seen by the network. So our network has to generalize to these new different objects that it might not have seen before. So for this problem, there's really two popular data sets. Davis, which is an older data set. So there's 60 training videos. 30 validation, 30 test videos, and those are annotated 30 frames per second. This is a rather small data set, but it seems to be like the most used, right? Because it was like the first video object segmentation data set. And then a newer data set which came out in 2018 is YoutubeVOS. Many times more videos. The only issue is they're annotated 6 frames per second, but you could easily get around this by interpolating annotations, or which is what we do in our work. But so this gives us a lot more data, so it allows for us to train deeper networks and allow us to train more deep learning solutions for this type of problem. So yeah, so here are some examples that might show the difficulty of this problem. So in this case we have to segment both the boy and the bicycle. So as you can see, the bicycle is rather small, especially as the person gets further away. In this, there's multiple trains, and as the orientation of the train changes, you have to segment the entire train still. And as you can see, in the people dancing there's many people. You have to segment only the ones, those 3 that are given, and then also the dogs example. And as you can see, the dogs move rather quickly, so it's easy for networks to lose that segmentation as they move quickly. So are there any other questions about the problem itself, or?
Excuse me, how do you get the loss function after the first thing? What's the ground truth?
The ground truth is a segmentation for the object. So we would be given, so let's say we're given this. At training time, we have the video as well as the segmentation for all the frames.
For the second frame, what will be your ground truth?
We have the segmentation for the second frame at training time. So we have the entire video and all the segmentations for all the frames at training time. At test time, we're only given the first frame. Yeah.
You might be asking, do you have the other frames for test time to evaluate your performance?
Yeah, at test time, we don't have. We submit the system. We submit our. Someone has the frames to evaluate. Yeah. No. All right. Okay. So now I'll get into the work. CapsuleVOS. So the idea behind this is, all right. As I said before, capsules model entities or objects, and routing by agreement finds similarity between these entities and objects. So this would be ideal in VOS because we could do the following, right? We can leverage those 2 ideas for VOS by first we extract capsules from the video and the segmented first frame. So we would have 2 sets of capsules. One would be the video capsules, which would represent the different objects within the video. And then we have the first frame and segmentation, so that would extract the object of interest, the one we want to segment. And then we could use routing by agreement to find the agreement between these 2 sets of capsules and end up with a single set of capsules which represents that object of interest throughout the video. So here's a description of what I just said. So we're given the video, we have some encoder, which can encode our video into a set of capsules, video capsules. So those represents let's say all the deer in this video. And then we have our reference frame and segmentation, right? So we have this segmentation and the first frame. We could have some encoder, which encodes this frame into a set of capsules, which represents only this deer, which is segmented, right? Because we're giving it this segmentation mask. And then we could use capsule routing to condition those video capsules to end up with a set of capsules which represents this deer, but throughout the entire video, right? I think my slide's messed up. Sorry about that. Okay. So yeah, it seems my slide's messed up, but basically what I just said, right? Let's move on. Okay. Yeah, so we're given, so we create the video capsules and the frame capsules, and what we do is the original routing by agreement only really, it doesn't do this type of conditioning which we want. What routing by agreement does is we have a set of, let's say, n capsules in one layer. We want to map them to m capsules in the second layer. And what it does is it just finds the agreement between all those capsules in the first layer. We technically don't want that, right? Because what we want is we want to find the agreement between this set of capsules here and the video capsules, right? So we want to find the agreement between this set and that set. We don't want to find the agreement between all the capsules, just put in a bag and get a final video capsule, final capsule representation. So, okay. So what we do is we implement an attention routing algorithm, which tries to basically condition the video capsules based on the frame capsules. Okay, so the way we do that is the following. So we have our video capsules and our frame capsules, and what we can do is we can use attention, which is a popular, basically what attention does is you get a set of values, keys, and queries. So from the video capsules we can get a set of values and keys, votes, and from the frame capsules we get a set of query votes, right? And so what these try to do is, we can do the following. First, we get our query votes, we perform the standard EM routing, and get a set of query capsules. So these query capsules represent the object in the first frame, and we can compare that object in the first frame with all the votes present in the video, right? So all the key votes. So if we can compare them, we can do the following. We could just compare them simply by measuring some Euclidean distance between each query capsule and the corresponding vote, and get some sort of distance matrix. And then using a softmax, right, we can find basically the attention. So we could find which key votes correspond to that object in the first frame, right? So which objects in the video, or which object in the video corresponds to this object of interest, and we could get some sort of attention map. So the darker blue would be closer to 1, so that would say, okay, that vote corresponds with that object, and then the lighter votes, the lighter colors would be correspond to 0, saying, okay, that vote does not correspond to that object, it corresponds to a different object. So those give us some routing coefficients, or assignment coefficients, which we can use for the routing algorithm for these votes. So given these assignment coefficients, we can choose which capsules are important from the video and only route those capsules to get our final set of conditioned video capsules. Right? And so what these capsules would represent would be the object of interest inside the video. Okay. So I'll briefly go over our algorithm. So yeah.
How are these key votes and value votes different from each other? Like,
yeah. So we have a set of video capsules, right, which are just activations, right, grouped activations. We have 2 different sets of weights, which are randomly initialized differently, so they learn to different things, right? So we have 3 sets of weights to learn those key, query, and value. So the weights learn what they have to learn in order to differentiate between each other, if that answers the question. Yeah. Yeah. Does that answer your question? Or?
actually, just wanted to know why this terminology, key and...
Oh, from the original Attention is All You Need paper, they use this terminology, key, query, and value. And I think that's based off of databases. They use that type of terminology in like database, so that's where they got inspiration from. So I'll briefly go over the algorithm we use. So our capsules are composed of the matrix M and the activation. So these are the video capsules. We have also the frame capsules, right, with poses M and activations A, and we have our set of weights, right, which transform these capsules into the votes. And so this is the algorithm that's in the paper. So first we generate the votes by doing a simple matrix multiplication between the poses and the weights. Then we perform EM routing on the query capsules, or the query votes, to get some set of query capsules. Then we perform this Euclidean distance and softmax operation that I talked about to find the similarity between the queries and the keys. And then we just obtain this routing coefficients. And then we finally use one M step, so one step of the routing algorithm to obtain our final capsule representation. So this is the overall architecture. I'll briefly go over the architecture, one step at a time. Okay. So first, the video encoder. We input a video clip of 8 frames by 128 by 224, which is the height and width, and then 3 channels into a set of 2+1 deconvolutions. So these are similar to 3D convolutions. The only difference is instead of having a 3x3x3 kernel, what you first do is do a 2-dimensional kernel and then follow that up by a 1-dimensional kernel in time. Right? So that's a 2+1 deconvolution. It reduces the number of parameters and is more efficient than regular 3D convolutions. And we find that in this architecture it actually worked better than 3D convolutions. So these 2+1 deconvolution gives us our video capsules. So we end up with this many video capsules, and there's 12 capsule types. So that's the video encoder. So now the frame encoder, what we do is we input the first frame in segmentation. So the first frame in segmentation is 128 by 224, and then there's 4 channels, the RGB and then the segmentation. So it's a black and white segmentation which we concatenate with that frame. We pass that through a series of 2D convolutions, and then we pass that through a memory module. So what the memory module allows us to do is remember, it's basically a Conv LSTM, but it allows us to remember the objects which may have left the scene or been occluded. Since our overall network just processes 8 frames at a time, when we process the first 8 frames, we'll output sort of segmentation. Then we have to process the next 8 frames and so on. So at one point in the video, the object might leave the scene, but we still have to process those 8 frames. So what the memory module allows us to do is remember what the object is, so that when the object re-enters the scene, we've still segmented after its occlusion or leaving the scenes. And then we end up with a set of frame capsules. So this many frame capsules with 8 capsule types. So we could say we model 8 different objects, object parts, you could say. Then we perform the attention routing, which I briefly went over. So we through the attention routing, we end up with 16 capsule types of this dimension. So in total is 4 times 8 times 14 times 16 different capsules. And then we finally pass that through a final capsule convolution layer, which is another routing by agreement layer, and a series of transpose convolution to end up with our final output segmentation mask, right, which is for a segmentation for all 8 frames at the original 128 by 224 resolution. And we have skip connections from the capsule layers, previous capsule layers, to maintain the spatial dimension, which might have been lost in the convolutional layers. So this is the overall network. One addition we do to deal with small objects is the zooming module. So for example, let's say we're given this as the first frame in segmentation. The segmentation is actually this person right here. which is quite small. If we were to just resize this to 128 by 224 and pass it into our network, the object of this object will be extremely small and the network would lose that object rather quickly. So what we do is we have a zooming module which inputs this first frame in segmentation and outputs a set of bounding box coordinates around the object such that we only have to focus in on this cropped region. And then we crop that region, resize it, and pass it into our network to obtain the segmentation for this region here. Right, as you can see, the input, now it's rather large, so the network can easily segment that object. And then once we have that object segmented, we can resize it back and place it back in the original frame. So this helps deal with this issue of small objects, which is rather prevalent in this data sets. So basically the zooming module is a set of 2D convolutions followed by an LSTM layer, which allows us to remember the object when it leaves the frame, and it outputs the bounding box coordinates. So I'll go over the objective function used to train this, but basically the zooming module has to not only zoom in on the object in the first frame, but it has to basically predict where the object will move in future frames, right? So it doesn't cut it off. Let's say after frame 6, it might move out of the bounding box. So it has to predict some larger area which the object may move to. Yeah.
When the object moves out of that original bounding box, is there a new one formed for future frames? Or
so if it moves out of the bounding box, then our segmentation will be cut off, right? Because it's not, the entire thing is not passed into the network. But that actually tends not to happen from our experiment, from my qualitative results at least. What it does is it predicts a large enough bounding box so that even if it moves quite a bit, it's still within that bounding box. Yeah. But yeah, that is something which could be looked into. So to train the network, we have 2 losses, well, 3 losses total, but for the CapsuleVOS network, the segmentation network, we use a binary cross entropy. So I don't know if you guys have gone over this, but basically we have some set of predicted output segmentation masks. So this is between 0 and 1, whether or not it's present at that pixel or not. And we have a ground truth. We have the ground truth segmentation for all the frames. And basically we just do the cross entropy over all the pixels of that 8-frame clip. And we also have a dice loss, which helps us with the, have finer grain segmentations. And then to train the zooming module, we just have an L2 loss, which basically is which predicts the height and width the box needs to be around the object of interest. So we have a predicted height and width, and then the ground truth height and width is basically the height and width necessary to encompass the entire object within that 8 frames. And then we add a little margin to make sure we don't cut off the object. And then the network is trained end to end just using the sum of these 3 losses. So we achieved state-of-the-art results on YoutubeVOS dataset at the time. So the overall score is 62%. And one interesting thing is it's much faster than the other previous methods that achieve state-of-the-art results. And the reason for this is since we're processing videos 8 frames at a time, we're able to basically segment videos 8 times, well, not 8 times faster, but much faster than the previous methods, which tend to segment objects 1 frame at a time. Yeah.
Is that inference or training time?
Inference time. Yeah. So we segment it about twice as fast and still achieve a significant margin over the other methods. And then here you can see a nice plot here of the speed versus performance. So at the time there was an online method, S2S, which is an LSTM basically, but it's online, so they have some training at the test time as well that's performed on the first frame. It performs about 2% better than our method. However, it's about 100 times as slow, right? So you can see that our method is quite good, right? Especially for the speed it has. So here's some nice qualitative results. So for these are all examples with just a single object of interest. As you can see, the boundaries around the object are rather good. So our network is able to segment these quite well. If you look at this example here, there's a lot of camera motion, but the object is still not lost. And yeah, in this example here, the fox moves rather quickly, and still our network is able to segment that quite well. So here's an example with multiple objects. So if you look at the top right, there's quite a few sheep that we have to segment, a flock of sheep, and the network is not distracted by the other sheep, which tends to happen in some models that do re-ID and things like that. So yeah, there's some more examples. So here are some examples. So I showed earlier that the network, the frame encoder, had a memory module. So without the memory module, we see that we want to segment this parachute, and after the parachute leaves the frame and re-enters, the object is lost. However, with the memory module, with that Conv LSTM, we're able to segment it even after it leaves the frame. So that's one example. Another example of occlusion occurring. So we want to segment that bear. So the bear goes behind the tree for about a second in the video, which is a rather long time. And when it reemerges, the network completely loses the object. But with the memory module, it's able to remember what the bear looks like, and it is successfully segmented even after a very long occlusion like that. So here are some examples of occlusion and how the network is able to deal with occlusion. So the panda is partially occluded, and it's still able to mostly segment it quite well, even as it crosses under the wood. And then also this person in the back is completely occluded by this other person, and even after the occlusion, it's segmented correctly. So the second thing we check is the effect of the zooming module. So this is the original first frame. As you can see, the objects of interest in this bottom right-hand corner are quite small, right? They probably take up less than 5% of the frame. If we look at that object of interest, if we don't have the zooming module, then we see even after 20 frames, we completely lose the ball, and then these segmentations are quite rough on these two people. And then by frame 90, we completely lose the two people on the two objects on the bottom. But with the zooming module, the segmentations are actually quite crisp, and we're able to correctly segment these objects even for the entire video. And then another example, this eagle or bird. After 30 frames, the segmentation is looking quite rough, and then after 95 frames, it's completely lost. But with the zooming module, we see that it's able to successfully segment this bird throughout the entire video. So here are some other examples of small objects being segmented quite well with the zooming module. So, yeah. And that's it, yeah. Yeah. So any questions? Or let me just keep this up. Yeah.
So, first of all, nice work. And I haven't heard much about capsule networking before, so it's quite interesting. It's the first time. One question that I had, if you can go back to the comparison table we had with other methods.
Sure.
The one-shot video object detection method seems to be better on the ANSI categories, and they do use the ImageNet pre-trained weights on the base network.
Right.
Do you think that's the reason that they have a little bit better on the ANSI category, or what's your thought about that?
That's one reason, and then another reason, I believe, one shot, yeah. So OSVOS actually does online training.
Yeah.
So it trains at test time on that first frame, so it is able to learn that object in the first frame at test time. We don't use any online training, so that's another reason why we might perform worse on unseen videos. Yeah.
Is the reason for no online training was for the computation time right in front?
Basically, yes. Yeah.
Alright, so I had something about, you go to the capsule networks diagram where you had capsule A, B, and C.
Yeah. The EM routing.
Yeah, I believe so.
This. Oh.
So before we answers that question, just give me.
Sure.
Okay, so
Yeah, just give me a minute. Sorry. So is Mahavir here?
Yeah.
Okay. And Tanuj? So you two are taking this class?
Yeah.
Alright, you haven't finished assignment 0. So just wanted to make sure.
Sure.
Okay. Sorry, go ahead.
Okay, so I think you mentioned that ideally you want them to overlap and highly agree.
Yeah.
But do different capsules not, are they not supposed to like model or maybe detect different features?
So each one of these 10 capsules may model a different feature, but their votes are basically their prediction on what capsule C would look like, right? So like let's say each one of these is a different feature of your face. Ideally, if they were to predict what your face looked like, they would all line up to be exactly what your face looked like, right? So capsule C, ideally they would all have the same prediction for that object, even though they model different objects within the different parts within the whole.
So it's like moving from low-level features to high-level features.
Right.
So you're not stacking the actual like capsule A, capsule B, that entire window. You're just kind of stacking like I guess the blue dots.
The blue dots. We want the votes to agree as much as possible.
Only the lower level capsules are stacked.
Right. The lower level capsules are the ones we're finding the agreement between. Right.
So higher levels are those A, B, and C. Yeah.
Just a simple question about title. So you are saying that it is semi-supervised.
Yes.
So like, are you using any label data in training?
No. It's semi-supervised because we're given the first frame at test time. It's a fully supervised method. The problem is called semi-supervised video object segmentation. I dislike the problem name, but that's what it's called. So, yeah.
It means no, like on application, you only need the first frame.
Right. Exactly.
I have a question about the overall system. Like
Yeah.
you mentioned that capsules are basically building on lower level features to.
So maybe this is about the architecture.
Yeah.
Or, this.
Yeah. So the capsule, the first capsule there actually appears after the whole CNN, right?
Right.
So at that point, the features that the CNN has are already very high level, right?
Yes. They're not edges, right?
On the capsule, but
Right.
in the original capsule paper, they have capsules even at the actual lower levels, right?
Right. They have it after one conv layer. They have a capsule layer, right? The issue is the computational complexity. If we just have one 2D, like let's say we have one 3D convolution and then a capsule layer, we would have much too many capsules to be able to compute, right? Because these 2 plus 1D CNNs have strides, so our dimension is going to decrease. And the second is it's going to be difficult to train that network.
Right, but my question was more that like the theory for why standard capsules work versus the theory for why this works, shouldn't that be different because the capsules are getting very different kinds of features, like they're qualitatively different, not just by macros?
Yes and no, because these features might be higher level, but the idea of parts to whole relationship, right, is still preserved here, right? So we would still have maybe these are high-level parts, right? They might not be edges forming into hands or forming into shapes. There would be parts of an animal forming into the whole animal, right? So that part-to-whole relationship is still there, even though we're not directly getting capsules from the very, low-level features. Yeah.
Yeah. The original paper was on MNIST, right? MNIST means what kind of features you want to extract? It's mostly like the edges, right? The direction where they are in. So probably like 2 or 3 layers is sufficient to get that information. And for images or videos, we are, as you said, like we are not looking into edges. It could be like your ear, so that's a complex object. So you might need like more layers to extract that kind of low-level features.
So these convolution layers, are they pre-trained or?
No, this is all trained from scratch. Yeah.
And the transpose convolution, what is the architecture?
Transpose convolution is just transpose convolutions. It's just 5 transpose convolution layers. It's like Conv, 3D transpose, and TensorFlow. I don't know. Yeah.
That you can also replace with like just standard convolution and then do upsampling.
Upsampling, yes.
On that matter, like the transpose convolution, you're reconstructing the output image, right?
Right.
Usually some methods for segmentation, they have the skip connection, so they bring back the low resolution, so you have a better reconstruction on the segmentation.
Right.
You guys are doing this, like when you do this like skip connection up there,
yeah.
Are you guys bringing back that low, like high resolution image to the transpose convolution as well?
To some extent. So we have only skip connections from the capsule layer.
That's already reduced, right?
That's already reduced, yes. It's reduced to about 1/8 the size, I believe, or 1/4.
Output mask are still high, like they're still good? Like,
yes.
Oh, that's
yeah. We actually found that if you have the skip connections from these 2+1 deconvolutions, so like maybe half the resolution, it actually performs worse. Because what it does is it doesn't learn the representation in the capsule layers. It starts learning some representation here, which we don't want this to learn. We want this to learn the best features possible for the capsules. So yeah, so if you add skip connections from here, it performs slower, right, because you have more parameters, and also we found that it did perform worse. Yeah.
That I think is a good point. So what you can try is, so right now, as you said, what's happening is if you pick features from those layers, then you're not interested in like all the objects. You are looking into one specific object which you are conditioning at this point. So if you can come up with a method to take those features at each layer and try to filter those features based on your object of interest, that might be useful.
Yeah, like if you use the zooming model and get just the like high resolution of that specific model, it might improve the output mask. Like, I don't know how you do it.
Okay, any other question? So how many of you read this paper before the class? So from like Thursday, you'll have to read the paper, right? So if you don't have any other question, then we can stop here. Right? Thank you.
What happened to my slides?